In our introduction to thermodynamics, we talked about work and heat. We've figured out a way to quantify work for pressure volume work, and we did an example. Now we're going to talk more about heat. And today we're going to look at how we measure and how we quantify heat. Calorimetry is the study of measuring energy that's gained or lost during some process through heating. So this could be a chemical reaction, it could be a physical change, it could be other things too. Calorimetry. Calorimetry depends on the thermal properties of materials. And there are two kinds of thermal properties. One kind is called extensive. Extensive properties of materials depend on how big they are. Heat capacity is an example of an extensive thermal property. Heat capacity is defined in words as the energy that's required to raise the temperature of an object by a certain amount. More useful probably is the equation version of this. If I take the ratio of the heat energy added to the temperature change, that's what heat capacity is. Units of heat capacity would be then joules, probably, over degrees C, or joules over kelvins. Those would be examples of units of heat capacity. Here's an example. A rock's temperature rises from 5 degrees C to 55 degrees C when 5,000 joules of energy are added. We're supposed to find the rock's heat capacity. Well, by definition, heat capacity is equal to the energy added over the change in temperature. So here, 5,000 joules were added, and the change in temperature, well, it went from 5 degrees up to 55 degrees, so that's a 50.0 degrees C temperature change. The units will be joules per degree C, and since this is a difference in temperature, I could also write joules per Kelvin. If I take 5,000 divided by 50, I get 100. To three significant figures, it's 100 with a decimal point. So 100 joules per degree C is the heat capacity of that rock. That depends on how big the rock is. If I took that rock and split it in half, well, the heat capacity would be split in half too. If I had twice as big of a rock made out of the same material, the heat capacity would be twice as big. Sometimes it's useful to have a property that doesn't depend on how big the object is if it's made of the same substance. So there are intensive properties as well, and specific heat is an example of an intensive property. Specific heat is the amount of energy that's required to raise the temperature of some unit of mass, so a small amount, of a substance by a certain temperature change. So in equation form, we could say specific heat, which is abbreviated C, is equal to the ratio of Q over mass times change in temperature. So this is heat capacity per unit mass. The units of this would be typically joules over grams, because that's how we measure mass, times a temperature unit like kelvins or degrees C. Here's an example problem. The temperature of 250 grams of water goes from 25 degrees up to 30 degrees C. How much energy was transferred into the water? Well, here's the definition. Specific heat is equal to Q divided by mass times temperature change. If we wanted to find out how much energy, it's Q that we're solving for. So we'll multiply both sides by mass times delta T and get this equation. Q is equal to C times mass times delta T. So now we'll plug our information in here. It tells us in the problem here that 4.184 joules per gram per degree C is the specific heat of water. I'm multiplying that by the mass of water I have here, which is 250 grams. And the temperature change, well, if it goes from 25 up to 30, that's a 5 degree C change. And I round it off to the 10th. What will happen to the units is grams will drop out of here, so will degrees C, and I'll end up with energy units, joules. To two significant figures, the numerical answer is 5,200 joules were added. In the introduction to thermodynamics, we talked about how the universe is divided into two parts. The system, which you're trying to study, and the universe. But the universe is an extremely complicated place. So in order to practically measure heat flows, we use a device called a calorimeter. And what this device essentially does is just restricts the universe into a manageable space. Here's how it works. Inside of a pot of water is the system. So that's the system. It could be a chemical reaction. It could be something else. And there are some pipes that go in here to illustrate how a chemical reaction could happen with some gases. That's not an important part of what we're looking at right now. Surrounding that system is a water bath. Well, water has known thermal properties. We know what the specific heat of water is. We could also use oil or something else. The key is that we know what specific heat is. Here, for water, 4.184 joules per gram per degree C. It's a well-known fact about water. So this is containing a whole pot of water. There's a thermometer in here too, so we can measure temperature change. So we'll have the reaction take place, temperature will go up or the temperature may go down, and we can measure here what delta T is. And then another thing that's important is there's a stir bar here. So this thing spins around and around and mixes the water so it's not like hot here and cold overboard when we're measuring temperature. So we keep a constant temperature throughout the whole thing. And then the real key to making a calorimeter work is the walls of this container are heavily insulated, and that keeps Q from coming in and out from the outside. There's no heat flow out or heat flow in for a short period of time. As long as you work fast and you have good enough insulation, the whole entire universe is restricted to what's inside this box, inside the calorimeter. It makes it possible to manage the whole idea of rest of the universe being the surroundings. So by observing the temperature change of the water, by observing this thermometer, and knowing the mass of the water, we'd have to have that, we can do this. Heat flow that comes out of the system, let's say that heat comes out of the system, sometimes it goes in. Heat flow is going to be equal to the specific heat of water times the mass of the water bath times the change in temperature that the water bath experienced. Now, if heat flows out of the system into the water, the temperature is going to go up. If heat goes from the water into the system, temperature is going to go down. Either way, you can read delta T, multiply by specific heat and mass, and you'll find out the heat flow. The system inside the calorimeter could have a constant volume. In other words, the reaction could be happening inside of a pot like this, whose volume can't change. Well, if that's the case, then delta V is 0. And so that means minus P delta V is 0. And so that means work is 0. And so that means all the energy that's exchanged here is in the form of heat. So when you measure the heat flow in a constant volume calorimeter, you're measuring the total energy change. If the system in the calorimeter has a constant pressure, in other words, volume can change, but the pressure is allowed to stay the same, then you have a different situation. Here, work is possible because minus P delta V will be a non-zero number. So that means because delta E is Q plus W, that delta E is Q minus P delta V. So if we solve for Q, what we're finding here is the total change in energy plus the pressure times the change in volume. So it's energy minus work. So if we have a constant pressure calorimeter, QP we can say here, we're not measuring the total energy of the system. We're measuring the amount of energy less the work that was done. This situation happens so often that the pressure is constant in a calorimeter that we've invented a new way of tracking energy at constant pressure. It's called enthalpy. When Q is measured at constant pressure, what we're measuring is delta H. H stands for enthalpy, and enthalpy by definition is E plus P delta V. So delta H is delta E plus P delta V, and that's constant pressure heat. So this is enthalpy change, or so if this is a chemical reaction, we abbreviate heat at constant pressure Q reaction, or we might say enthalpy change of reaction. That would be the symbol for enthalpy change of reaction. Enthalpy is what's called a non-sensible quantity. It's not something that you can directly experience. It's defined by a calculation. You can measure it because you can measure Q for the reaction. But to get a physical, intuitive idea of what it is not so easy. If the system loses energy to the surroundings, in other words, the water bath in the calorimeter experiences an increase in temperature, that is a change that's called an exothermic change. For example, a campfire would be exothermic. If I burn something, it gives off heat to the surroundings. That's exothermic. It's easy to remember this if you know that therm is a word that means heat or energy, or sometimes temperature, it's misused. And then exo means out. Like in biology classes, you may have learned about exoskeletons. Those are skeletons that are on the outside of the animal. So exothermic literally means heat out. Here's an example of an exothermic reaction. 0.220 grams of propane reacts. It's inside a constant pressure calorimeter. The water bath weighs 250 grams. Its temperature goes up by 10.6 degrees C. What is Q reaction for the process? What we're trying to find is Q for the reaction. Q for the reaction is going to be measured by what happened in the calorimeter. And specific heat times mass of the water times the temperature change of the water bath is how we're going to measure that. So, Q reaction for this particular reaction is equal to specific heat of water, of the water bath, 4.184 joules per gram per degree C, times the mass of the water bath, that was 250 grams, times the temperature change of the water bath. Well, it says it rose by 10.6 degrees C, so that's delta T. This will end up being joules, and the answer to three significant figures is 11,100 joules. This question is asking, in the previous example, how many kilojoules of heat were released per mole of propane? And propane is C3H8. Well, if we want kilojoules per mole, first we're going to have to take our joules and convert them to kilojoules. Well, if we need kilojoules per mole, the first thing we need to do is have our energy in kilojoules. So let's convert that. 11,100 joules. I want this to end up in kilojoules. There are 1,000 joules per 1 kilogram joule. So when joules cancel out, I'll be dividing by 1,000. It's 11.1 kilojoules. Now I also need to know how many moles of propane were burned up. Well, there were 0.220 grams of C3H8, and I want to know how many moles that is. I'll do that with molar mass. The molar mass of propane works out to 44.097 grams per mole. When I do this division, I get 0.00499 moles of propane. So, kilojoules per mole, it's 11.1 kilojoules per 0.00499 moles, and that works out to 2,220 kilojoules released for every mole of propane. For the system, that would be a negative number because the propane gave energy off to the surroundings. For the water, that's a positive number, the surroundings, because energy was given to the surroundings. If the system gains energy from the surroundings, in other words, the water bath's temperature goes down because it lost energy to the system, then that's called an endothermic reaction. And if you think about endo, like an endoskeleton, that means in, and therm, remember, is heat or heat energy. So this is a heat-in reaction. An ice pack would be an example of that. A reaction happens, it gets cold, feels cold because it's taken energy out of you and into itself. Here's a numerical example. 18.015 grams of ice melts inside a constant pressure calorimeter. Water bath is 250 grams. The temperature drops by 5.75 degrees C. What's Q reaction for this process? Well, to find Q, again, we're looking at the specific heat of the water bath times the mass of the water bath times the temperature change of the water bath. Specific heat for water is 4.184 joules per gram per degree C. The mass of our water bath here, again, is 250 grams, like in the previous example. And the temperature change, well, it says the temperature dropped by 5.75 degrees C. So this will give us energy units because grams and degrees C cancel out. And when we calculate it numerically, we get 6,010 joules. Now here, we would express Q as a positive 6,010 joules. And the reason that we use positive here is because the system actually gained energy. It takes energy to melt ice. This temperature of the water bath went down, and so we know that we have an increase in energy inside the system. Because the water bath lost energy, the system must have gained energy.